All right, this is the first presentation of chapter 13, the first out of two presentations. This chapter is focusing on solutions. As a preview of what this chapter, we will be learning in this chapter is we'll be learning about solutions, and these are homogeneous mixtures. Then we'll be learning about solutions specifically of solids in water. We'll be learning about what solubility is, what saturated solutions are of solids in water, a specific type of solution where we have electrolyte solids in water, and then how solubility depends on temperature. Then we'll be learning about solutions of gases in water. Then we'll be looking at different ways of reporting solution concentration. One is mass percent, one is molarity, and one is molality. Then we'll be looking at the dilutions of solutions, then the freezing point depression and boiling point elevation, and then osmosis. So in West Africa, in Lake Nyos in Cameroon, it was struck with a tragedy in 1986. So Lake Nyos is a water-filled volcanic crater. And the molten volcanic rock beneath the lake that we see here, it produces carbon dioxide gas. And that carbon dioxide gas slowly seeps into the lake. Well, normally, the high pressure that's created by all the water that's on top of the lake, or that makes up the top portion of the lake, it holds down that CO2 that's created, and so that CO2 remains at the bottom of the lake. That CO2 and the water that's at the bottom of the lake is a type of solution. Well, what happened in the summer of 1986 is that the layers in the lake were disturbed, and they ended up decreasing the amount of pressure that the top of the water, or the top water, was actually putting on the bottom of the lake. And with a decrease of pressure, much of the CO2 that was held at the bottom of the lake suddenly began to be released from that solution. So what ended up happening is that carbon dioxide ended up flowing into the adjacent valley. And this is a sudden great amount of carbon dioxide that's now floating into the valley, and it displaces the air, and then it ends up having deadly consequences. About 1,700 people and 3,000 cattle died from this exposure. Now scientists have built a piping system, and this slowly vents out the carbon dioxide from the bottom of the lake, and it prevents future catastrophes as what happened in 1986. So that carbon dioxide and water mixture that was at the bottom of Lake Nyos, that was an example of a solution. A solution is a homogeneous mixture that has two or more substances. So solutions are very common. Most of the liquids and gases that we encounter every day are actually solutions. The ocean, for example, is a solution that's made up of salt and other solids that's dissolved in water. Blood plasma is a type of solution, and it has several solids as well as some gases that's dissolved in water. So again, solutions are homogeneous mixtures of two or more substances. A solution is made up of two parts. A solution will have one or more solutes, and it will have a solvent. The solute is the minority component. The bigger component in the solution is called our solvent. Table 13.1 lists some common types of solutions. So if the solution phase is a gas solution, the solute and the solvent are both gas. Air, for example, is a gas solution. It's made up of mainly oxygen and nitrogen gas. We can have several different types of liquid solutions. We can have it so that the solute, the minority component, is a gas, but our solvent needs to be a liquid. We can have it so that our solute is a liquid, but again, our solvent needs to be a liquid. And we can have it so that the solute is a solid, but our solvent is a liquid. So as long as our solvent is a liquid, it is a liquid solution. And then we can have solid solutions where we have both the solute and the solvent as solids. Now, in a solid liquid solution, the liquid is usually considered the solvent, even if in some case the solid ends up making the majority component. In that case, that's one of the exceptions. The liquid is usually considered the solvent. Now, we've heard this term before, like dissolves like. Well, in terms of solutions, that means that polar solvents can dissolve polar solutes, and nonpolar solvents will dissolve nonpolar solutes. But polar solvents and nonpolar solutes will not dissolve, and nonpolar solvents and polar solutes will not dissolve. So again, like dissolves like. Depending on if you have the first scenario with a polar solvent and a polar solute that's forming a solution, then our solution is polar. If we have a nonpolar solvent and a nonpolar solute that makes up the solution, then our solution is nonpolar. Here, table 13.2 lists some common laboratory solvents. On the left side, we see common polar solvents. And on the right side, we see common nonpolar solvents. Water is very often the polar solvent that we encounter. But we can also have a polar solvent of acetone or methyl alcohol. Some nonpolar solvents are hexane, diethyl ether, and toluene. Now, we mentioned this before, that much of the solutions that we see have a solvent, the polar solvent, water. Now, on Earth, because water is so abundant, it is a common solvent that forms a specific title to that type of solution. So when we have a solution that specifically has the solvent water, we give that solution the phase name aqueous. Now, to form a solution, the solvent-solute attractions have to overcome the solute-solute and solvent-solvent attractions that were already formed. So for example, if we had a beaker of water and we're adding sodium chloride, the ionic compound sodium chloride to it. Well, in order to dissolve, we must break apart some of the attractions that are holding some of these water molecules together or next to each other. And we must break some of the solute attractions that are holding the sodium ion and the chloride ion together. So these attractions, these new solvent-solute attractions, must overcome these solvent-solvent attractions between the water and the solute-solute attractions between the sodium ion and the chloride ion. So here we see, initially the beaker only contained water, but then we placed sodium chloride. And sodium chloride is actually in a crystal form, or what we consider a lattice. Well, when we put it into water, because it is soluble in water, it actually dissociates into the individual ions. So here we see in purple are the sodium ions, and in the green are our individualized chloride ions. So the new attractions that are forming are our ion dipole attractions. For example, the chloride ion has a negative ionic charge, which is attracted to the partial positive charge of each of our hydrogens in H2O. Similarly, our sodium ions have a positive charge, and they're attracted to the partial negative charge of our oxygens in H2O. Now, the solubility of a compound is defined as the amount of that compound, usually in grams, that's able to dissolve in a certain amount of liquid. So, for example, the solubility of sodium chloride, which is table salt, at room temperature, 25 degrees Celsius, its solubility is 36 grams of sodium chloride per 100 grams of water. So if we formed a solution that contained 36 grams of sodium chloride, or table salt, in 100 grams of water, that is considered a saturated sodium chloride solution. So a saturated solution holds the maximum amount of solute, which in this case is sodium chloride, under the standard or under the solution conditions. So in this case, our example is that we can have that our saturated solution for sodium chloride is 36 grams of sodium chloride per 100 grams of water. So if we were to already have a solution that has 36 grams of sodium chloride in 100 grams of water, and we tried to add more of our solute, our sodium chloride, into this already saturated solution, that additional amount will not dissolve. An unsaturated solution, however, holds less than the maximum amount of solute. So for example, if we had a solution made where we only had 20 grams of our sodium chloride in 100 grams of water, then this would be an unsaturated solution because it holds less than the maximum amount of sodium chloride that could be in that could be dissolved in that 100 grams of water. So if we were to have a solution that contains 20 grams of sodium chloride in 100 grams of water, and we were to add more of our sodium chloride solute into this unsaturated solution, that additional amount of sodium chloride that's being added, it will dissolve because we hadn't reached our saturated solution yet. In some cases, we can form what is considered a supersaturated solution. And a supersaturated solution, it holds more than the normal maximum amount of solute. So the solute will normally precipitate from or come out of a supersaturated solution. And supersaturated solutions can only form under certain special circumstances. Now we have seen this table before, table 7.2 in chapter 7, and it's looking at the solubility rules. These solubility rules give us a qualitative description of the solubility of ionic solids. So for example, or for this top part of our table 7.2, and the bottom part, from this we're able to see what ions are soluble in with other ions. So for example, if we look at calcium carbonate, is CaCO3. This is an ionic compound that has the ion calcium 2+ and the ion CO3 2-. So we see here that we have carbonate ion here, and it says that that compounds containing the following ions are mostly insoluble. So CO3 2- is mostly insoluble, except when either of these ions pairs, then the compound will be soluble. Well, if we find calcium 2+ in that list, that means it would be soluble. But calcium 2+ is not on that list, so it's not one of the exceptions. So CaCO3 will be insoluble. So calcium carbonate is an insoluble compound. That means that the attraction that's between the calcium ions and the carbonate ions is greater than the solvent-solute attraction. Because of this, calcium carbonate will not dissolve in water. So only when we can have the solvent-solute attraction actually be greater than the solute-solute attraction and the solvent-solvent attraction, then we can form a solution. But in this case, it's the opposite. So we do not form a solution. So what ends up happening is that calcium carbonate will not dissolve in water. So the solubility of calcium carbonate is close to 0 grams per 100 grams of water. And so we just say, like we do in this table, that it's insoluble. Molecular solids can also be soluble in water. depending on whether that solid is polar or not polar. Table sugar, for example, if we were to draw this out, we would see that it's actually polar. And because it's polar, and because water is polar, table sugar will actually be soluble in water. However, where we have non-polar solids, such as lard or vegetable shortening, because these are non-polar, they will be not soluble or insoluble in water. Now, depending on the solute that's dissolved in water, or in our water, they can be either considered electrolyte or non-electrolyte solutions. So we can have an electrolyte solution if what dissolves is dissolved ions. And dissolved ions means that they're charged particles within water. For example, when we dissolved sodium chloride, an ionic compound, they split into, the sodium chloride structure split into sodium positive ions and chloride minus ions. These are charged particles. So this forms an electrolyte solution. And with these charged particles, they're able to conduct electricity in the solution. We can also have non-electrolyte solutions, and these contain dissolved molecules. These are molecules that have no overall charge or neutral particles. And because they have no charge, they do not conduct electricity. Now, looking at how solubility varies with temperature, generally, the solubility of solids in water will increase with increasing temperature. So we see different ionic solids that are shown here, and we see that as we're increasing temperature, their solubility is increasing. The y-axis here is the solubility, specifically in how many grams of the solute will be dissolved or is dissolved in 100 grams of H2O. So for example, if we look at lead nitrate, we see that at 0 degrees Celsius, about 37 grams of this ionic compound will be able to be dissolved in 100 grams of water. As we increase temperature to let's say 40 degrees Celsius, we see that about 76 grams of lead nitrate will dissolve in 100 grams of water. Let's look at this diagram and see how we can use it to answer a question. So at 30 degrees Celsius, a solution contains 30 grams of potassium nitrate per 100 grams of water. At this temperature, is the solution unsaturated, saturated, or supersaturated? Well, let's first find at this data point. So we're at 30 degrees Celsius, and we're trying to find the line that represents potassium nitrate, which is this green line. So at 30 degrees, what's represented at where this temperature hits this curve, this is the amount of grams of potassium nitrate that can be maximum soluble in 100 grams of water. So the point at which it hits the graph represents where it is saturated. And it would be saturated at 30 degrees, where we have about 45 grams of potassium nitrate in 100 grams of water. Now, in this question, we have less than 45 grams because we're only reporting 30 grams of potassium nitrate in that 100 grams of water. That means that we could still add another about 15 grams and still have it be soluble. So this data point here for 30 grams of potassium nitrate represents an unsaturated solution because we could still add more of our solute and have it be soluble. So the answer here is that the solution is unsaturated. So again, anything below the line at the temperature is considered unsaturated. At the line at the temperature is considered saturated, and anything above that line at that temperature is considered supersaturated. Now we can use this temperature dependence of solubility to purify compounds. A common way to purify a solid is a technique that we call recrystallization. With recrystallization, we put the solid into water. So if we've formed a solid product, but there could be some impurities in that product, what we do is we put that solid into water or some other solvent at a high temperature. So here enough solid is added to the solvent to create a saturated solution at that high temperature. Then we let that solution cool. So now the temperature slowly decreases. And as we saw on that last curve, as temperature decreases for most ionic compounds, that means that the solubility also decreases. Because the solubility decreases, that'll cause some of the solid to precipitate from that solution. Precipitate means that it'll come out. So it was soluble, but now some of that solid is going to form a solid again and actually separate itself from the rest of that solution. So as long as we're letting the solution cool down slowly, then the solid will form crystals as it comes out. And these crystalline structures are good at rejecting any impurities, so anything beside that pure product that we wanted. So because it rejects it, that solid crystalline structure is more so just your pure solid, your pure product. We can use this recrystallization technique to make rock candy. To make rock candy, we can prepare a saturated sucrose solution. So that means a saturated table sugar solution at a high temperature. Then if we dangle a string into the solution and then just let it cool and stand for several days, then as the solution is slowly cooling, it's becoming supersaturated. And with that, sugar crystals actually grow onto that string. Now, as we said before, the water with the carbon dioxide gas that was at the bottom of Lake Nyos is an example of a solution. It's an example of a solution where we have a gas in water, not solid in water. Soda pop is another example of a solution where we have gas dissolved in liquid, water. In both these cases, our gas is carbon dioxide dissolved in water. Actually, most liquids that are exposed to air contain some amount of dissolved gases. Lake water and seawater, for example, contain dissolved oxygen that's necessary for the survival of fish. Our blood contains dissolved nitrogen, oxygen, and carbon dioxide gases. And even tap water contains some dissolved atmospheric gases. Now, opposite to the solubility of solids in water, where we're looking at the solubility of gases in water, will actually decrease with increasing temperature. We can see this by heating ordinary tap water on a stove. Before the water reaches its boiling point, we'll start to see some small bubbles that are starting to develop in the water. And these bubbles represent some dissolved, represent the dissolved air, which is mostly nitrogen and oxygen gas that's coming out of the solution. So as we continue to heat this, more and more of these nitrogen and oxygen gases, these gas bubbles, will go to the top of the water and actually escape the liquid water. Once the water boils, the bubbling then becomes very vigorous, and these larger bubbles are composed of water vapor, not just dissolved air. So that means after we reach the boiling point, that's where we're having our liquid phase of water convert into gas phase of water. So these larger bubbles are actually composed of water vapor, which is now separating from the liquid water. Here we see the example of solubility of gas actually decreasing with increase of temperature. We see on the left side, we have cold soda pop. And in cold soda pop, we have more carbon dioxide that is more likely to stay in the solution, versus when we have warm soda pop, the carbon dioxide more rapidly leaves the solution. Because again, as temperature increases, the solubility of gases decrease. Now, the solubility of gases and liquids can be described by Henry's law that looks at the pressure of the gas above the liquid. Henry's law states that the higher the pressure is above the pressure of the gases above the liquid, the more soluble the gas will be in the liquid. So if we look at these two pictures, on the left side, in comparison, we see less amount of pressure, and for that reason, we have less amount of solubility of that gas in the liquid. Whereas on the right picture, we see a higher amount of pressure of gas above the liquid, and therefore we have a higher solubility of the gas within the liquid. So again, Henry's law states that the solubility of a gas in the liquid will increase with increasing pressure of the gas above the liquid. We see that here too, in a closed can of soda pop. In a closed can, majority of our can is our liquid solution that has gas dissolved in the solution. But at the very top of our can, we have a certain amount of non-liquid, just gas that's above the liquid. As we open up the soda can, all of a sudden, this amount of non-liquid gas, so non-dissolved gas that was just sitting at the top, a lot of that will escape. This now decreases the amount of pressure that's above the liquid. And because we have decreased that pressure, now the dissolubility of the gas is also being decreased. Now there are different ways to report the concentration of solutions. One is reporting mass percent. Mass percent is the number of grams of the solute per 100 grams of the solution. So for example, if we have a solution with the concentration of 14% by mass, that means that we contain 14 grams of solute for every 100 grams of solution. So to calculate mass percent, we divide the mass of the solute by the mass of the total solution. And remember, solution is made up of both the solute and the solvent. So that means that we divide the mass of the solute by the mass of the solute plus the mass of the solvent. And then multiply that by 100 because this is the percent. In addition to parts per 100, which is percent, also in common use are parts per million, ppm, which is the number of grams of solute per 1 million grams of solution. And also another common unit is parts per billion, which in this case would be the number of grams of solute per 100 or per 1 billion grams of solution. Let's take a few minutes and try out some of these problems. And then we'll do number 1 together. Here we want to calculate the concentration of each solution in mass percent. In number 1, for example, we have 41.2 grams of C12H22O11. That's dissolved in 498 grams of water. Please pause the video as you try this problem. And let's do this together. First, let's recall what mass percent is. Mass percent is going to be equal to the mass of your solute per mass of the solution. And then again, because this is a percent, we have to multiply this by 100. So in this case, for number 1, we know that C12H22O11 is our solute, and H2O is our solvent. Because, as we said earlier, normally the amount that's greater will be our solvent, and the amount that's less will be our solute. So the mass of the solute we know now is 41.2 grams of C12H22O11. And we need to put this over the mass of the solution and multiply that by 100. Remember that our solution is made up of both the solute and solvent. So for a mass of our solution, that'll be the mass of our solute plus the mass of our solvent. And lastly, multiply that by 100. And our answer comes out to 7.64%. Now we can use the mass percent of a solution as a conversion factor between the mass of the solute and the mass of the solution. In order to use it as a conversion factor, we can write the mass percent as a fraction. So if we had 1%, 1 mass percent, that would mean 1 gram of solute per 100 grams of solution. If our mass percent was 70%, or let's say 7%, it would be 7 mass percent is equal to 7 grams of solute over 100 grams of solution. Here's an example where we use mass percent as a conversion factor in our calculation. So in this problem, a water sample from the bottom of Lake Nyos contains 8.5% carbon dioxide by mass. We want to determine how much of the carbon dioxide in grams is contained in 28.6 liters of the water solution. So what we're given is that we have 8.5% carbon dioxide by mass, which again, we've learned we can rewrite that as a conversion factor shown here, which is 8.5 grams of CO2 per 100 grams of solution. We're also given that we have 28.6 liters of solution and that the density of our solution is 1.03 grams per milliliter. So we start off with 28.6 liters of solution, convert that into milliliters. So we cancel out our liters, and we've now converted into milliliters of our solution. Then using the density, we can cancel our milliliters and convert into grams of our solution. And then using that conversion factor of the mass percent, we can then cancel out our grams of solution and end up with just grams of that carbon dioxide. And we get 2.5 times 10 to the third grams of carbon dioxide. Let's try a problem. where we're determining the mass in grams of each sodium chloride solution that contains specifically 1.5 grams of sodium chloride. And for each of these, we are given the mass percent of sodium chloride by mass. Pause the video as you try this. All right, let's do this together. If we have 0.58, well, we'll just do number one together. So if we have 0.58% sodium chloride by mass, that means that that's equal to, we're given the amount of our solute, or sodium chloride, so that's 1.5 grams of our sodium chloride, and we're trying to find per how much mass of our solution. So we want to solve for mass of solution. So the first thing we'll do is we will multiply mass of solution on both sides of the equation, so that we get rid of it being on the denominator of one side of the equation. So now we have mass of solution times the 0.058. Oh, I'm sorry. This is all multiplied by 100 in the first equation. So if we multiply mass of solution times 0.058%, that's equal to 1.58 or 1.5 grams of sodium chloride times 100. And then to get to mass of solution by itself, we'll have mass of solution equal to the 1.5 grams of sodium chloride times 100 divided by 0.058%. And we get that the mass of the solution is 2.6 times 10 to the third grams. Now another unit to specify the concentration is molarity. And molarity is defined as the number of moles of solute per liter of solution. So molarity is the short way of writing it is uppercase M, and that's equal to the moles of your solute over liters of the whole solution. To make a solution of a specific molarity, we'll normally have to put the solute into a flask first, and then start adding water until we have the desired volume of solution. Which is what we see here. Here we're trying to prepare a 1 molar sodium chloride solution. So again, first we will add our amount of our solute. In this case, to prepare a 1 molar sodium chloride solution, we can add 1 mole of sodium chloride, which is 58.44 grams. And then we'll slowly start adding water. First, we'll add just a little bit of water and stir it around until all of our solute has been dissolved. but then we'll need to fill the water up until the 1 liter mark, which is shown here, to have overall a 1 molar NaCl solution. Let's look at an example problem for calculating molarity. Example 13.3 of your textbook. We want to calculate the molarity of a solution made by putting 15.5 grams of sodium chloride into a beaker and then adding water to make 1.50 liters of the sodium chloride solution. So in order to calculate the molarity, we need to identify what we're given, what we're trying to find. We're given that we have 15.5 grams of sodium chloride, which is our solute, and we have 1.50 liters of the entire solution. And we want to find the molarity. The first thing I propose to do is remember what we're trying to solve for. We're trying to solve for molarity, and molarity means that we're trying to solve for the moles of our solute per liter of our solution. So we'll need to find the moles of our solute over the liters of our solution. So we have 15.5 grams of sodium chloride, but we need to convert that into moles. So we'll multiply 15.5 grams of sodium chloride by the molar mass, and that'll cancel out the grams of sodium chloride and convert into moles of sodium chloride. And we get 0.2652 moles of sodium chloride. Now we have the moles of our solute and we have the liters of our solution. So now we can just plug that in, the moles of solute over liters of solution, to get our answer of 0.177 moles, or molar, or molarity of our solution. Here's another example problem. Here we want to determine how many grams of sucrose, C12H22O11, are contained in 1.72 liters of 0.758 molar sucrose solution. So we're starting off with liters, and we have the molarity. And with the molarity, we're able to cancel out the liters of solution by multiplying the volume of solution times the molarity. So that cancels out the liters of solution and converts into moles of our sucrose. And then lastly, we want to determine how many grams of sucrose are needed, not just how many moles. So lastly, to convert moles into grams, we'll use the molar mass. And that's what we see at the bottom here. We multiply the 1.72 liters of solution by its molarity to cancel out the liters of solution and convert into moles of sucrose. And then lastly, multiply that by the molar mass to cancel out the moles of sucrose and convert into grams of sucrose. And we get 446 grams of sucrose. Now, the reported concentration of a solution that contains a molecular compound reflects the concentration of the solute as it actually exists in the solution. So that means for a molecular compound such as glucose, if we have a 1.0 molar glucose solution, that means that that contains 1.0 moles of glucose for every 1 liter of solution. However, the reported concentrations of a solution that contains an ionic compound reflects the concentration of the solute before it's dissolved in the solution. So if we have a 1.0 molar carbon chloride solution, CaCl2, that means that it contains 1.0 moles of the calcium ion per every 1 liter of solution. And that also means that it contains 2 moles of the chloride ion for every 1 liter of solution. That's because these chloride ions will separate, and in the ionic compound, there was 2 chloride ions for every 1 ionic compound. Let's look at an example problem, example 13.5, at calculating the ion concentrations. Here we want to determine the molar concentrations of sodium and phosphate ions in a 1.50 molar sodium phosphate solution. So we're given that we have 1.50 molar sodium phosphate, and we want to find the molarity of the sodium ions in the solution and the molarity of the phosphate ions in the solution. So what we see is that for every 1 mole of ionic compound, or for every 1 molar of the ionic compound, sodium phosphate, there would be 3 moles of the sodium ion, or 3 molar sodium ion. So in order to determine the molarity of the sodium ions, we would multiply the molarity of the entire ionic compound by 3, and we would see that we have 4.50 molar molarity of the sodium ion. We also see that for every 1 mole of the sodium phosphate ionic complex, or ionic compound, we have 1 mole of the phosphate ion. Therefore, whatever the molarity is, the 1.50 molarity of the sodium phosphate ionic compound, that'll be the same as the molarity of our phosphate ion. Now let's try an example problem where we're calculating the molarity of each of the solutions. Let's try numbers 1 and 2. Notice we'll do numbers 1 and 2 together, but I also recommend trying numbers 3 and 4 for practice. For numbers 3 and 4, it'll be similar to what we're doing for numbers 1 and 2, except that you're starting off with grams of your solute. And to get your molarity, you will need to convert that into moles of the solute. Take a few minutes as you try these 2 problems. All right, let's start off with number 1. First, let's remember what molarity units are required. Molarity, or the big M, is looking for the moles of solute over liters of solution. So for number 1, we're given that we have 0.127 moles of sucrose, which is our solute, in 655 milliliters of solution. So the molarity here would be our 0.127 moles of our sucrose over the 0.655 liters of our solution. And we get that we have 0.194 molar solution here. Let's try number 2. In number 2, we're just trying to get the molarity of the whole solution. And we're given that we have 0.205 moles of potassium nitrate in 0.875 liters of solution. Again, we already have our moles of our solute, and we have the liters of solution. So we'll just plug that in to the molarity equation, which is the amount of moles of our solute, which is 0.205 moles of the potassium nitrate, over the amount of liters of our entire solution. And that gives us 0.234 molar solution of sodium nitrate.